Have you ever wondered how YouTube somehow loads your videos instantly, even when billions of people across the entire world are watching at the exact same time? I mean, really think about that. Picture a planet filled with people pulling out their phones, their laptops, their TVs, from Sao Paulo to Seoul, from Nairobi to New York, all tapping that little red play button. And somehow, almost miraculously, the video begins playing in what feels like a fraction of a second. It's easy to take that for granted because it feels so normal, but it shouldn't. The amount of engineering, coordination, calculation, prediction, and raw computer power required to make that happen smoothly is absolutely staggering. YouTube moves more data than almost any other product on the internet. It handles the weight of the world's attention every single moment. Yet it manages to deliver video with a level of smoothness that honestly borders on science fiction. But what if I told you that this smooth, effortless experience is the result of a relentless, ongoing battle fought behind the scenes? A battle that happens over microseconds, over cache lines, over memory tiers. And that this battle is so sensitive that changing a single decision in the caching system can ripple out across the globe. Because yes, that's exactly what's happening. The engineers behind YouTube constantly push their systems to get just a fraction of a percent better. Just a hair faster. Just slightly more efficient. And here's the part that almost nobody knows. One of the biggest improvements to that system came not from adding more servers, or rewriting everything from scratch, or inventing some new hardware. It came from a subtle, clever, surprisingly small machine learning model called HALP, short for Heuristic Aided Learned Preference Eviction Policy. And this little algorithm has quietly been deployed across the entire global YouTube CDN, improving performance for over 2 billion users every single day without anyone realizing it. So today, we're going to unpack exactly how that works. Because HALP is not just another academic idea. It's not a simulated toy model. It's one of the rare papers where the idea actually made it all the way into production, at a scale that almost no ML system ever reaches. It's like discovering there's a tiny AI living inside YouTube's memory systems, constantly making decisions thousands of times per second, influencing what stays in the fast lane and what gets pushed out. If any of this sounds complicated, don't worry. I'm going to walk you through it step by step. Even if you've never thought about caching, memory hierarchies, or machine learning, by the end of this video, you'll have a deep intuition for how YouTube keeps up with the entire world's video appetite. But before we dive in, hit that like button, subscribe, and leave a comment that says, "Help the algorithm," because it genuinely helps more people discover these deep dive breakdowns. And trust me, you don't want to miss the videos coming up next. Okay, let's take a journey inside YouTube. I want you to imagine a giant globe. Now, sprinkle hundreds of dots across it, big dots in cities, small dots in rural regions, clusters everywhere from Tokyo to Toronto to Tunis. Each of these dots is an edge cluster, a mini data center filled with machines that store and serve YouTube videos to viewers nearby. The whole point of distributing these clusters around the world is simple. The closer the video is to you, the faster it loads and the smoother it plays. Now zoom in on one of those clusters. Imagine racks and racks of servers, metal boxes stacked like skyscrapers of silicon. Inside each server are multiple layers of storage, DRAM, SSD, HDD. And above all of them is the heart of this system, YouTube's DRAM cache, the fastest, most expensive, most precious tier. If your video's data is in DRAM when you request it, boom, you get instant playback. If it's not there, well, then YouTube has to go digging downward, first into SSD, then HDD, and if it's really unlucky, all the way back to the origin servers dozens or hundreds of milliseconds away. That's when you start seeing buffering. That's when things feel slow. So YouTube's goal is pretty straightforward. Keep as many relevant video chunks as possible in DRAM for as long as possible, without wasting space on something that won't be requested again. And this is where things start to get tricky. DRAM isn't just fast, it's small. Incredibly small relative to the tidal wave of data flowing through YouTube every second. Even with terabytes of DRAM, it fills constantly. So YouTube has to evict something over and over and over again. Every time a new chunk arrives, an old one must go. Imagine playing a game where every decision has to happen instantly, and the wrong choice, even slightly wrong, can break the entire flow of the system. That's YouTube's caching problem. For years, YouTube used heuristics to make these decisions. Algorithms like LRU, or least recently used, look at which chunk hasn't been accessed for the longest time and kick that one out first. It's simple, fast, predictable. Other heuristics like ARC or TinyLFU do more sophisticated tracking of recency and frequency. But here's where reality breaks the simplicity. YouTube's workload is messy. It's unpredictable. It's constantly shifting. People binge-watch shows in long sessions. Kids replay their favorite scenes over and over. Entire regions suddenly swarm to a viral music video. A gaming streamer goes live and traffic surges in minutes. Patterns evolve like weather systems. Heuristics, which assume that the near past predicts the near future, often get blindsided. Machine learning sounds like the obvious solution. Learn the patterns, predict the future, know which chunks will be used again and which won't. Simple, right? Except, no. Because at this scale, ML is expensive. A previous ML-based algorithm performed 64 predictions per eviction. That added nearly 20% CPU overhead. Imagine taking a system that powers nearly 1/3 of the internet's video traffic and suddenly giving it a 20% tax. Unacceptable. This is where HALP enters the story, and honestly, the elegance of this solution is beautiful. HALP doesn't throw away the heuristics. It doesn't say, "We're smarter now, get out of the way." Instead, HALP works with them. Think of the heuristic as a scout, a fast, cheap filter. Before HALP even sees the eviction candidates, LRU or another heuristic narrows down the entire cache to just 4 objects. 4. That's the equivalent of having a librarian narrow down thousands of books to just a handful before asking you which one to return. Once HALP has those 4 candidates, it runs a tiny neural network, one hidden layer, nothing fancy, to score them. Each object comes with a set of features: how long since it was last accessed, how often it has been accessed recently, a signal about whether the end of the video chunk was just reached, and a set of exponential decay counters that capture long-term trends. These features fit into a very small input vector. The neural network produces a score. HALP then takes those 4 scores and performs a mini tournament of pairwise comparisons. Picture HALP holding a tiny bracket tournament inside YouTube's memory system, where each comparison takes nanoseconds, and the winner is the chunk that HALP predicts is least likely to be needed again soon. That chunk gets evicted. But the true genius of HALP is not the scoring, it's the learning. Traditional ML systems require large offline training datasets, big training pipelines, scheduled retraining. HALP doesn't need any of that. It trains itself online, in real time, directly inside the YouTube CDN. Every pairwise comparison HALP performs becomes potential training data, but it only becomes labeled once one of the 2 chunks is requested again in the future. So HALP keeps these comparisons in limbo. As soon as one of the compared chunks gets requested, HALP updates the label. Once it accumulates 1,024 of these resolved comparisons, it retrains itself automatically. No human intervention, no batch jobs, no heavy compute requirements. HALP is a living system, constantly adjusting its internal model to match the behavior of actual viewers around the world. There's even a ghost cache, where metadata for evicted objects is kept around temporarily, so HALP can still learn about objects that have already left DRAM. Now, all of this sounds great in theory, but YouTube's biggest challenge wasn't building HALP. It was proving that HALP actually works at global scale. And here's something truly surprising. Even servers sitting right next to each other in the same rack behave differently. Identical hardware, identical configuration, same region, same cluster, different workloads, different access patterns, different fluctuations. So if you simply A/B test the system, the natural noise might completely hide the effect of HALP. You might think HALP is worse when it's actually better, or vice versa. To solve this, the YouTube team built a clever statistical framework called impact distribution analysis. Instead of looking at one number, like average improvement, They look at the full distribution of improvements across many racks. They isolate noise by using a third group of machines that run the baseline algorithm but are treated as the noise sample. Then they mathematically deconvolve that noise from the HALP results. Once they did this, the true impact became clear. HALP reduced YouTube's DRAM byte miss ratio during peak hours by 9.1% on average. That is massive. At YouTube scale, that is monumental. Fewer misses means fewer trips to SSD or HDD. It means lower latency. It means smoother playback. It means fewer expensive origin fetches. But it gets better. Disk first byte latency dropped by 3.8%. Join latency, the time between tapping play and seeing the first frame, dropped by around 1.2%. And the CPU overhead for all of this? Just 1.8%. Think about that. For under 2% additional CPU usage, YouTube gets a global, measurable, consistent improvement in user experience, performance, and resource usage. In simulations, where noise doesn't exist, HALP outperformed classic caching algorithms like LRU, FIFO, and ARC on more than 92% of traces. It matched or exceeded state-of-the-art ML-based approaches while requiring only a fraction of the compute. And the best part? HALP has been successfully running in YouTube's production environment since early 2022. It is already live. YouTube may be playing you a video right now using this algorithm. What I love about HALP is that it is the perfect embodiment of practical engineering. It doesn't try to be flashy. It doesn't assume ML solves everything. It doesn't replace heuristics. It augments them. It uses just enough intelligence to outperform heuristics, but not so much that it becomes slow, unstable, or risky. HALP is thoughtful, elegant, efficient. It is machine learning used not as a magic wand, but as a scalpel, precise, targeted, safe. And the result is a YouTube that is faster, smoother, and more efficient for billions of people. If you enjoyed this deep dive into the algorithm quietly making YouTube faster, hit that like button, subscribe, and leave a comment telling me which system you want me to break down next. We're building a library of the hidden technologies that quietly run the world, and your engagement tells the algorithm to keep pushing these videos out to more people. Thanks for watching, and I'll see you in the next one.